This episode is brought to you by Cisco Educational Premium.
The gravitational pull of a neutron star is remarkably potent as well. Dropping an object from 1 meter above its surface would cause it to hit the star in 1 microsecond and accelerate to a velocity of 7.2 million kilometers per hour. The surface of a neutron star displays an exceptional flatness, with irregularities not surpassing 5 millimeters. It possesses an extremely thin atmosphere of hot plasma. The neutron star surface reaches approximately 1 million Kelvin, contrasting with our star temperature of 5,800 Kelvin. The crust is incredibly solid and likely composed of ion atom nuclei lattice and dispersed with a sea of electrons. As we approach the core, the number of neutrons increase while protons decrease, eventually resulting in an immense mixture of indistinguishable neutrons. The core of neutron stars remains enigmatic and mysterious. Although we haven't fully grasped their properties, the prevailing belief suggests that they may be composed of superfluid neutron degenerate matter, or an ultra-dense quark matter called Quark Gluon Plasma. These peculiar states of matter defy conventional understanding and can only thrive in ultra-extreme environments. In many aspects, a neutron star bears resemblance to a colossal atomic nucleus, distinguished mainly by the forces binding them together. Atomic cores are governed by strong interaction, while neutron stars are governed by gravity. If it weren't already extreme enough, let's explore some other attributes. Neutron star exhibits incredible fast rotation, with young ones spinning several times per second. If a nearby star is unfortunate enough to be captured by neutron star gravitational pull, it can accelerate its rotation to several hundred times per second. As in the case of PSR J1748244-6AD, which spins at an approximately 252 million kilometers per hour. This rapid rotation leads to a peculiar star-shaped. We designate these objects as pulsars due to their emission of strong radio signals. Additionally, the magnetic field of a neutron star is approximately 8 trillion times stronger than Earth's magnetic field. This magnetic force is so potent that it bends the path of atoms as they come under its influence. The observable universe, with its vastness, is hard to grasp, and according to certain theories, it may be relatively insignificant. Current calculations indicate that the unobservable universe could even be larger, possibly exceeding 20 trillion light years in diameter. Despite its enormity, much of it might be empty, similar to the scarcity of observable universe. Matter composed of countless atoms is incredibly small, beyond the resolutions of our most advanced microscopes. Scientific evidence confirms the existence of atoms consisting of subatomic particles like protons, neutrons, electrons, and quarks. Astonishingly, there are theories suggesting that everything, including humans and entire observable and unobservable universe, could be akin to an atom in a grand reality. One such concept is a one-electron universe theory, suggesting that what we perceive as multiple electrons might stem from just one particle moving swiftly back and forth in time, creating the illusion of many. Speed mirage. Thinking loudly again. Although this theory lacks scientific support, it serves as a starting point for other similar ideas with more backing. A more mainstream variation is rooted in the multiverse theory, proposing that All atoms, electrons, and properties of matter in our universe could be equivalent to an atom in a larger universe. This idea has been explored in science fiction, where our universe is seen as a mere speck in a higher plane of existence, or where each atom within us contains all other existences. Infinity plays a vital role in these concepts, suggesting that no matter how vast our universe is, if the multiverse theory holds, there could be infinitely larger universes, making us appear subatomic from their perspective. Observing the universe, we see how tiny subatomic universes come together to form increasingly larger structures from celestial objects to complex organisms. This leads to the question on whether the universe itself could be part of something greater. The blurring of micro and macro levels cannot be disregarded until we have a comprehensive theory of everything. This will unify quantum and classical physics. According to the popular theory of the universe creation, it began as an infinitely dense singularity before expanding through the Big Bang, implying that everything we know was once inconceivably small. However, it is important to note that the initial singularity contained the necessary components for the formation of atoms, distinguishing it from an actual atom. Although these ideas challenge our understanding of reality, they serve as thought experiments to contemplate our place in the vast cosmos. While they might be mind-boggling, they do not diminish the wonder and significance of our existence. String theory is considered one of the most leading contenders for the theory of everything, aiming to understand the true nature of reality. In this theory, atoms are not depicted as spherical objects, but rather as string-like structures that vibrate, responsible for all interactions of the universe, including the laws of physics, gravity, and quantum mechanics. However, string theory faces challenges, particularly concerning dark energy, which constitute a significant portion of the universe. Most string theory models struggle to explain the dominance of dark energy compared to observable universe and compared to observable matter. Some recent attempts have been made to incorporate dark matter into string theory. These include variations proposed by researchers from Uppsala University in Sweden. This variation suggests that our universe exists on an edge of constantly expanding bubble where everything we know is merely a small component of something much larger. Inside the bubble and beyond its edge, a known dimension might exist, and the infiltration of dark energy from the wider bubble universe could provide a better explanation. If this version of reality was accurate, it would drastically change our current understanding of science. It would place human beings as infinite small parts within a much larger, grander, and incomprehensible structure. However, it is essential to recognize that this idea is merely a thought experiment, a fun way to ponder our place in the cosmos. Even if our perspective prove limited and our knowledge flawed, the insignificance from another viewpoint does not necessarily diminish the value of our existence.
This episode is brought to you by Cisco Educational Premium.
For ages, it has been said that mathematics is the mother of all sciences. All the concepts of science stem from mathematics. This alma mater, the nourishing mother. Mathematics is truly astounding. And what better concept to demonstrate this than the birth of light as a consequence of solving Maxwell's equations? Maxwell's equations are four in number. The first is the Gauss law for electricity, which relates the net electric flux to the net enclosed charge. The second is the Gauss law for magnetism, which relates net magnetic flux to the net enclosed charge. The third is the Faraday's law, which relates induced electric field to the changing magnetic flux.
And the last but not the least is the Ampere Maxwell law, which relates induced magnetic field to the changing electric flux and to the current. But wait, Caleb. What they call Maxwell's equation again? That's a story for another day. Now, the real deal. This is a math show. We're not going to just make sense of statements, but crucially piece together reality from numbers, from mathematics. No shortcuts. These are Maxwell's equations in their differential form. In a vacuum, when there are no electric charges and currents, our Maxwell's equations will evolve to as shown. Our equations are now simpler. The first and the second equations are the divergence of electric and magnetic fields. These two are telling us that if there are no charges present to create magnetic and electric field lines or terminate them, there will be no divergence. The fields will be continuous. They will not start or end. Astonishingly, Maxwell's equations, even in completely empty space, can define and allow the existence of magnetic and electric fields. The other two equations deals with how these continuous electric and magnetic fields behave. The third tells us that the electric field can be created by firings of magnetic fields in the vicinity. Same as the third, the fourth equation tells us that we can get some magnetic fields in the vicinity by firings of magnetic fields. Both of these fields must be at right angles to one another for one of these fields to generate the other. Say in the third equation as shown, remember mathematically, the left hand side of this equation, del cross E, we are taking the curl of this. We are taking the cross product. Any factors within the cross product will always be completely at right angles to the resultant factors, which in our case is the magnetic field. So if the electric field points anywhere in the xy plane, the magnetic fields must be at right angles to it. The same thing goes for the fourth equation. Any change in the electric field causes new magnetic field at right angle to the electric field. Remember, we are solving Maxwell's equations. Now I want to find electric and magnetic fields formulas, so that when we substitute the left hand side, it will match the right hand side of these equations. We want the third and second equations. Remember, we can't get information about electric field without knowing the value of the magnetic field, and we can't get any information about the magnetic field if we do not know the value of the electric field. So what gives? These equations seem to be conjoined and tangled, so to speak. In math talk, we can say that it is a first order coupled differential equation. What we want to do is to decouple these equations so that they will be completely separate equations. A separate equation for E and a completely separate equation for B. Decoupling them, so to speak. Now, let us start with the fourth equation. Let us take the curl of both sides of this equation, and so we get as shown. On the left side, let us use the factor identity, so we get as shown. On the right hand side, let us exchange the order of the derivatives. Now replacing del cross E using the third Maxwell's law, we get as shown. Now combining everything, if you didn't notice, we have successfully decoupled the two equations into a second order linear partial differential equation. Just to review, the left hand side is the Laplacian operator, del square B, which is a factor 2, same as the right hand side, ignoring mu naught and epsilon naught, we have as shown. And so since both sides are factor quantities. The x component of the left hand side must match that on the right hand side. The y components must match too. Same goes for z. Just to remember, we are now finding the solutions to the second order decoupled differential equation. As we had seen, these really three separate equations. One for x, one for y, and one for z. Now we are going to try some functions on how they will solve our equations. Not that we are trying trial solutions for the x component, which is just the same for the y component, and so for the z component. Now I want to look for a function f that might obey the equation as shown, with alpha just a constant. Say partial sub t square f was just proportional to the original f, and similarly for partial x square f, we want to look for a function whose second derivative is equivalent to the original function apart from e to the x, so to say. Can you remember any? Yes, any cosine or sine function fit here. Partial t square cos t is equivalent to negative cos t. We are going to allow for f to have both an amplitude and frequency. F is equivalent to a cos omega t, where we have omega to be the angular frequency in radians per second. So if we have partial x square bx to be as shown, and if both partial x square bx and partial t square bx are proportional to bx, then we are on the right track. We know that partial x square a cos omega t is equivalent to 0. So we need to add some spatial dependence, some x, so to speak. We are going to propose an ansatz, a trial solution, so to speak. For those who took differential equations classes, I know this word, ansatz, went on top of our heads. It's just an example solution, a trial solution. The product of a function that depends only on space times a different function that depends only on time. Looks like the good old chain rule is in our favor. If partial x square fx is proportional to fx and partial t square gt is proportional to gt, that is, they are sine and cosines, then we have partial x square bx as shown. Also, partial t square bx as shown. And so we see that partial x square bx is proportional to partial t square bx, which is exactly what we need. Now, let us consider these two functions, our separable solutions. F is the frequency that is waves per seconds. K is the number of waves per meter. You can think of Kx as the spatial frequency analogous to Ft, which is the time frequency. Now, calculating the derivatives of our two functions. We have partial x square fx and partial t square gt as shown. And so if our magnetic field is expressed as bxxt as shown, provided by our ansatz, then we have partial x square bx and partial t square bx as shown. But let's just check. Our guess bxxt is as shown, with partial x square bx to be as shown. So it's okay. And so now we need to ask ourselves, does this obey the second order linear partial differential equation resulting from Maxwell's equations? Is partial x square bx as shown? Now replacing partial x square bx and partial t square bx with expressions as shown, but the left must match the right. So cancelling terms, we get as shown. And so the question we need to ask, does our ratio match the actual numbers of mu naught, epsilon naught, and the units? Then those are the exact function that are gonna solve Maxwell's equations. Now let us just look at the units of the ratio f on k as shown. This means that our f on k represents a velocity. Isn't it incredible? And so letting f on k be equivalent to v, then our equation will be satisfied when f on k square is equivalent to v square, which is equivalent to 1 on mu naught epsilon naught. Then what is the exact value of v? We know that mu naught is the permeability of free space, a magnetic constant, and it has a defined value. And epsilon naught is a dielectric permittivity of free space, and it too has a determined value. And so we are able to find the value of v, and we find it to be 2.998 times 10 raised to 8 meters per second, which is what? Which is the speed of light. This is the solution to the Maxwell's equations. The speed of light is the solution to the Maxwell's equations. The only solutions to Maxwell's equations have the property that they propagate at the speed of light, which are combination of magnetic fields and electric fields orthogonal to one another, carrying with them energy at that specific velocity, which is the speed of light or any electromagnetic radiation specifically. It is not only light that travels at that speed, all electromagnetic radiation specifically. And so James Clerk Maxwell created light, at least mathematically. Whether this was just a coincidence or a deliberate attempt, it doesn't matter. What matters is that it is correct. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.